guys, more here going. Another YouTube video.
So fucking with me. It didn't do that last time at all. Oh, fuck, stop. I'll do this. Hopefully it just. Nope, and it's still. Alright, whatever. Where were we? All right. One more thing. Winding the coil in layers. Plus minus. Winding the core in layers.
Plus.
So more layers is more inductance. Okay. So more layers make a greater effect of magnetic field on the conductor, which results in more inductance. Figure 11 has illustrations of this stuff. If you want to look more into it, I feel like it's pretty straightforward. All right. Voltage and current in an inductive AC circuit. The self-induced voltage across an inductance, which is L, is produced by a change in current with respect to time. So time is written either of these are acceptable. What is the triangle?
Delta.
Okay.
What is that?
Trust me, I took calculus in college. I know what delta means.
So
Delta T is changing.
this would be a change over time.
What is delta I?
Same thing. I is also for time. Either one works. No, sorry.
I'm about to say. I don't think.
Never mind. That was a formula. So, sorry. This is the voltage. For some reason,
Silly goose.
when they do it like this, they wrote it in lowercase. So, self-induced voltage across an inductance L is produced by a change in current with respect to time. So, change in current, change in time.
Oh,
Okay. So the formula for that is going to be this is called subscript. I don't know why you're nodding while you're not looking.
I saw what it was, and I looked down the formula again to look at it. I know what a subscript is.
All right, we're doing story commentary. So how do you read this then?
V to the subscript L. I don't know how you would say it.
No.
V to the L. It has no. That's just the way to identify the V.
Okay, so this entire thing we're doing is for L, which is self-induced voltage, which means this is the symbol. So V is still volt. V for volts.
But you're finding the self-induced.
The subscript is letting you know that it's self-induced voltage. That's going to equal inductance Yes, inductance. This is your formula. So your self-induced voltage is your inductance times your change in current divided by your change in time. So what the formula does is it gives you the voltage in terms of how much magnetic flux is cut per second. So do you understand what it means by that?
Yeah. Wait, what did you say?
So this gives you the voltage in terms of how much magnetic flux is cut per second.
Is cut?
Yes, magnetic flux. So remember, cutting the magnetic flux with a conductor is how you generate voltage. This creates magnetic flux in the conductor. When it expands, it cuts across other conductors. So this tells you how much voltage is created in those conductors from this magnetic flux cutting across them.
Yeah.
Yes? No? Questions?
Oh, it's a question. Yes.
Okay. Induced voltage across the coil is the result of inducing electrons to move in the conductor, so there is also current. So examples. We have self-induced voltage. Across 4 Henry inductance produced by a current of 12 amps per second. So
48 volts.
seasonal number. Blah, blah, blah. Yeah. Or did you just remember that from the book? Because I did use the same example.
I wrote it down.
Okay. Great. Now explain it.
Basically, plug all that into that.
All right, come do that.
Womp womp. What out of your face?
Real quick.
Speak while you do it. Explain it.
Induced voltage.
Mhm.
Self-induced voltage equals 4 Henry
Oh, here.
times.
You didn't write the H.
Yeah.
So I don't know what that is.
Weird. Do it right, man. Come on. 12 ampere seconds. 12 amp per second. 1 second.
12 amps
Or
per
in-
second. Yeah.
12 amps. Self-induced voltage equals 3 amps. This is one thing I could do all day. You give me some random formula, some random numbers, I can do that now. I don't know what it means, but
Okay.
I mean I know it.
Ty, grab a marker.
I did just so everyone knows go further than him in math. I don't know if you count one.
So the symbol for micro looks like this.
You also didn't do
Fires. So your example is find me the current through a 200 microhenry inductor. Hold up. Okay. Changes the current through a 200 microhenry inductor inductor changes from 0 to 200 milliamps in 2 microseconds. What is the induced voltage?
Microseconds in this.
And this is.
So there's my two numbers.
Say S. You need the S. This only means micro.
There's my two numbers.
The current through a 200 microhenry inductor changes from 0 to 200 milliamps in 2 microseconds.
200 milliamps.
Mm-hmm.
What's a milliamp? I write. What's the symbol?
And
Lowercase.
you said you understood it. Don't look over here.
I'm looking at the equipment.
Mm-hmm.
To play the equipment. I didn't say I memorized it.
Mm-hmm.
If I could jack this up. But my self-induced voltage would be this. Oh crap! I hit.
King Henry died.
It's probably way wrong. But B is equal to 200.
200 what?
King Henry died. Mr. Henry died. Are you gonna change it?
What?
That's micro.
Huh? I'm so good.
That's like your. Are you gonna change it to Henry or you just want to
It's the H.
micro?
I'm so confused. I told you something.
King Henry died. Freaking drop a bill. Write the acronym out.
Stop saying that. Just
I don't
say
know.
that.
Is that the same thing as? I don't know that.
Kilos. All right, let me stop.
Wait, does this have to be seconds for the equation work? Does this have to be Henry's? I'm asking.
They all have to be the same.
So that would have to be micro.
Or the micros would have to be milli.
But what's the multiplication factor?
It's 10 micros to a milli.
10 micros to a million. This is a milli.
No, that's a micro.
What is this?
Milli.
So there's 10 millis in a micro? 10 micros in a milli.
Yes.
There's 10 micros in a milli.
Yes.
10 micros in a milli.
Come on, Mr. Ridiculous.
10 micros. Okay, so just add a 0.
No. That's the micro. I mean, that's the milli. Sorry. It's 10 micros in 1 milli.
Add a 0. Add a 0.
There you go.
No.
No. You take away a 0.
I just added a 0 to here.
No, you didn't.
And then you said no. So I added a 0 to here.
No, you subtract the 0 from the micros to make them. No, oh my god, now you got me confused. Sit down. I sit the fuck down.
I just told you I would do that. I didn't have to do stupid conversions like this in my calc class.
That's so stupid. Why don't you know it?
Because it was hard and I didn't need it for what I thought I was going to do in college. So I flushed it down the toilet.
You flush basic math down the toilet.
Calc 1 is not basic math. I need the
is.
domain. Oh, this?
Yeah.
Yeah, no, I didn't need this to be a what was I going to be
All right, so we got 200 milliamps.
occupational therapist.
200 microhenry. And then in 2 microseconds. So what is our base voltage? We don't know, but it's going to be 200. It's not. See? Maybe 200 microhenry times 200 milliamps divided by 2 microseconds. So the way they want you to do it in the book is use scientific notation. So this is basically 200 times 10 to the minus 6 henries times 200 times
Oh, so they convert it back
10 to the negative third amps.
Okay.
And then 2 times 10 to the negative 6 seconds. It's the math on that calculator for.
Oh, what's the math?
Yeah.
Yeesh. Gosh. I would have written it out in normal person terms.
Okay, write it in normal person terms then.
Why is it? It's going to be a big negative number. It's going to be.
It's gonna be negative?
No. Forgot how to do that. It's that calling. Hello? Hi. We can do that. Alright. Alright. See. Good. I'm glad. No.
To the math. So 1 milli is 1/1000th. 1 micro is 1 millionth.
So they converted it back to.
They used scientific notation. You could also just.
I was just gonna leave it in.
You could just take the micro and to convert it to milli, you just
get your answer and then convert the milli.
1, 2, 3. So 0.2 millihenry, then 0.02 seconds, but then you gotta do more math to get it to blah blah. But yeah, it's 20 minutes.
Okay. I knew that.
Uh-huh.
They're gonna amaze you with my knowledge.
So you can't do that calculator as a test.
Okay, I'll just do them over. You can't use a scientific calculator on the test.
They might let you if there's one like built into the thing, but you're not allowed to bring any of your own stuff to the test.
Learning. How many tries do we do on the test?
You can take it 3 times in a year.
Same test all 3 times.
Yeah, so induced voltage. Is it a real voltage?
Is that a real voltage?
Is it a real voltage?
What is real voltage?
Can you use it to power something?
This
You
voltage.
measure it. If you touch it, does it shock you?
Mm-hmm. I don't think so.
No. It is. It's a real voltage.
That's the question.
And it can be measured.
It can or can't?
Can be measured. But the only time it exists, the only time it can be measured is when the current is changing. So when delta I over delta T is present for only a short time, induced voltage is in the form of a voltage pulse. What does that mean?
Is that the peak on the graph?
So, sort of. You remember when I showed you that DC line and like the sudden line up and then continuing? That would basically be one of those pulses because it's just one quick change and then no more change. So this is figure 12. I'm going to draw this for you. You don't really have to look at it. All right. Which one is voltage? Which one is current?
Red is voltage, blue is current.
Why?
Because the red leads.
So the way this works, induced voltages is as so the reason this is going up isn't because this is going down, because this is changing.
Mm-hmm.
So as it changes, this starts going up. And it peaks where this thing dips to its lowest point. And as it starts changing towards the maximum again in the opposite direction, then this comes down. Because now, remember, what decides is the direction of change. So this was going in the positive. Sorry, this was going in the negative. This is going down, which is why the amperage is going up.
So are they
This-
not in phase?
Hmm?
Are they in phase or not in phase?
They're not in phase. No, they're 90 degrees off phase. So the reason amperage is positive here is because this entire voltage line from here to here is a negative change.
Mm-hmm.
So even this part where it's in the positive is still a negative change because it's going from the max to 0, and then from the 0 to -0. And on the other side, now the amperage flips because now this is a positive change from here to here, here to here. Why is current at 0 even though the voltage is at max? Again, so back to the rate of change. The rate of change causes the induction. It's not the voltage that you put into it. It's not the amperage or the conductors or anything. What decides induction is how fast it changes. So the rate of change causes induction, and the rate of change here is 0. That's why your value here is 0. And the way to think about this is so now which parts of the graph are going to have the fastest rate of change? Let's see.
At zeros.
So let's say we split each of these parabolas into thirds. So each of these travels the same amount, like time. Each of these is the same time increment, right? But in this first time increment, change that much.
Mm-hmm.
In the second time increment, you barely did anything.
Mm-hmm.
And then in this last one, you changed a lot again, just in the opposite direction.
Uh-huh.
So that's that. When I say it's based on the rate of change, this is why. Because this first part has a high rate of change. That's why this peaks.
Gotcha. So when each one is at its greatest rate of change, that's when the other peaks.
Yeah. So imagine like when you throw a ball in the air. Before it comes back down, there's like a little second where it kind of hangs, right? Where like the gravity and the force of you tossing the ball out canceled out, so now it's just sitting there at zero. It's basically the same thing here. So like imagine like if you're standing on a truck and you throw the ball straight up in the air, obviously to you it looks like it went up and back down. But if someone's watching you, what they see is they see the ball move in an arc,
Yeah.
as the truck drives.
Mhm.
So you can think of it as the same way. So once it gets this, like the wave is going to pick up speed as it approaches these sections here, and then not really pick up speed, but the amount of distance it covers in the same amount of time is greater. So it's technically picking up speed, but not really. Like it's the metaphor. Until it gets to this point where it starts to slow down until it hits that peak. And then it's gonna have a pause at the peak and then start coming back down. Everybody good with that explanation?
We're live. I said
Why does
tip
this
to
thing
tip.
keep moving?
You're just so beautiful. It just wants to capture all of that fancy. You're a sight worth beholding.
All right. So does everyone understand why the polarity switches where it does?
Yes.
Why? Don't say yes if the answer is no. You said yes. Why?
You said what? Because it changes zero. It crosses zero. Crosses the horizontal axis.
What was the question?
Yes, that's why it's literally zero. But what makes it have a negative value? Me drawing it on the graph. didn't
When
give
the
it a
little
negative
thingy
value.
spins around, when it's upside down, when the capacitor is upside down.
What?
Whenever it passes 180 degrees.
All of you said yes, and you were all lying.
I didn't say yeah. I didn't say that.
Fine, you two are liars. Okay.
Just now remembered how to do math for scientific notation. So I'm
All right. So one more time.
now locked into.
You start with your voltage,
Mm-hmm.
and it, for the sake of argument, it's starting at the peak. Technically, it would have started earlier, but whatever. It's starting here. And it's coming down to the 90, right?
Mm-hmm.
During that time, the amperage is increasing, and it maxes out at the same time that the voltage hits zero. Now, at 90 degrees, that means the magnetic field. So during this part, the magnetic field was expanding. So it was crossing the other conductors in one direction. Now that you've crossed the zero line, that magnetic field is now collapsing.
Mm-hmm.
So now it's cutting the conductors in the opposite direction.
Mm-hmm.
So now your amplitude, your amperage is going to start coming down and going into the negative.
Mm-hmm.
So it's like when I drew that diagram over there and I had the left and right, and I told you that's what the sides, whether it's positive or negative, which way it cuts across. It's the same thing. but now it's the magnetic fields themselves moving out and coming back.
Expanding and collapsing with a magnetic field.
Yes, when it expands, positive. When it contracts, negative. Not necessarily. Like it could be the other way, but that's
what causes.
yeah. The point is like since the magnetic field expands in one way, positive, expands the other way, it's moving the opposite direction. The effect is the opposite charge.
Just a different way.
Cool. All right. And or conductor presents to the flow of AC.
Yeah.
Because of more sensitive.
You made us do Mario Kart and now brains told.
You know anything? I gave you a break. 4.5 hours without break.
4.5. I mean, if I got Mario Kart, Donkey Kong, I would be pretty fried.
Why can't an inductor start with what's resistance? Yeah. For the specific enough definition is the result of in the conductor. So why result of friction with. So if that's what we're, why can we not call for an AC resistance?
Friction.
Within nor inside the conductor. Inductance is neither friction, and it's not inside. So induction. So you can't count. This is and outside of the conductor. I don't know, maybe. What is that called? Instead of resistance, what's it called? Types. So next, when it's capacitive, it is X subscript C. When it is inductive, subscript C for capacitance. O for yep. All the reactance is the of the inductor to AC. measured in ohms. Realize inductive is 2 times induction. It's inductional too.
A circle.
So that would be
Your inductive rate, inductive. The only two things see and your inductive. Inductive rate, inductance. 20 Henry inductance.
Uh, 7,540 ohms.
Close enough. Probably round it a little bit.
I mean, 7,539.8223686155.
Once you have inductance, you can use it. You can basically just use it interchangeably as resistance in a form of Ohm's law. I equals E over XL. What's the I in this case?
here current.
It is not current. It is current, but it is not just current.
Current induced.
It is.
That was not me, that was Hayden.
It is effective current.
Oh.
What is the E type?
The E is your voltage. Your effective voltage. Yeah.
Is volt.
Unlike a resistor, there is no power dissipation in an ideal inductor. Why?
You say that again?
Because it's using all.
So in a perfect resistor, whatever you plug into it, it will stop all of it. Right?
Okay.
There will be, you plug one end to the one end of the resistor, you plug the other end to the ground.
Current comes in, doesn't come out.
There will be no current, period. So that's a perfect resistor. Unlike a resistor, there is no power dissipation in an ideal inductor. Why?
As in, power comes in, power goes out. Second.
Is that what power dissipation is?
Well, you just said that the one is power comes in.
Yeah, but the reason nothing comes out the other end of that perfect resistor is because it's 100% dissipated, meaning it's all used up.
Oh. So read the question again?
Unlike a resistor, there is no power dissipation in an ideal inductor.
It's not all used up. Is that what you're saying?
How much of it is used up?
None.
I would say wherever the device is.
So an inductor An inductor will limit the amount of current, but it does not use any net energy. So any energy that goes into it
Comes out.
gets back. So remember when I was explaining RMS voltage to you guys last week, and you asked me what about the rest of it? That's the rest of it. It's used to maintain the inductive field. So, in short, the energy required to build up the field gets put back into the circuit. I hate it when it cuts off right as I'm swiping, because then it becomes like a.
You said that last week.
I have amazing. Caleb, just watch last week's video and like redo this week's, and if there's anything you're not getting, you can just meet up with me.
Yeah.
We are on page 8 of 26. We are nowhere near closing remarks.
Dude, my feet are so cold.
Can I DoorDash or a pizza?
I've been here for
Honestly,
3
yeah,
hours.
sure, I don't care.
We've been here for 3 hours.
Wait, how much longer do we have?
Another hour
7.
and a half.
I'm not leaving here at 7:30. I'm leaving at 6:30. 3 hours.
Class is 4 hours.
3 hours. You told us 3 hours.
I said 3 to 4. This one's 4 because there's a lot to go over. There's a certain amount of time your ass has to be in that seat if you want your journeymans. And that's regardless of. That's why you clock in on the thing, and that's why I'm running out of time with breaks. You need 604 hours of your ass in that seat to get your apprenticeship license.
604.
You told me Mike did all that?
Well, technically, wouldn't we like?
He did it twice. He did 2 apprenticeships for some reason.
Wouldn't like 151 of those just like not count? Or since we didn't. Like,
You get credit for that. Through the NCCER.
yeah. So
All right.
really, it's only like.
What's a capacitor?
3.
What is a capacitor?
A device that stores electric charge in a dielectric parentheses insulating material.
One more time.
A device that stores. Bro, you're so gay. A device that stores electric charge in a dielectric material.
Okay. Let me give you a little bit better.
That's what the book said.
I know.
Amar.
A passive electrical energy storage device
That's battery.
containing 2 metal plates
Like an AC battery.
capacitors are not AC.
It's like a DC battery.
All batteries are AC.
Like a battery.
Alright. A passive electrical energy storage device containing 2 metal plates separated by a dielectric material. So you got your capacitor. Perfect square. You got a dielectric material separating the 2 halves. You got a metal plate over here. And you got a metal plate over here. Simple.
What is it, Hermes? What is that?
Herms?
Yeah.
Herms.
I think that's what it's called.
Herms.
Farads.
No, that's something else.
Herms. What the fuck is a Herm?
It's the one of the like terminals on the capacitor.
Oh. We're not talking about. Shut up. Alright. What's that electric?
Non-conductive material.
Insulate.
Well, same thing.
What is capacitance?
The ability to store the charge.
Ability to store charge.
In a capacitor. Voltage. The ability to store a charge in a capacitor. That is important when you're talking about capacitance. It produces an opposition to voltage change, and the unit of measurement is a farad. Which is a capital F.
Farquad.
Farad. If you does the term Faraday cage mean anything to you?
Yeah. Does the what?
Does a Faraday cage mean anything to you?
Faraday cage?
Yeah. You can basically
Diddy cage?
you can
Sorry.
you can build you from all like electromagnetism because the cage is grounded and a closed loop. So any electromagnetism that hits it gets absorbed and rerouted to the ground. So you can use that to like block out radio signals, telephone signals,
EMPs.
If you have a good enough one, yeah, a Faraday cage, named after the guy who made it.
Something. Faraday bag.
Hey, we make a Tesla cage.
Yeah, that's pretty cool. Well, look at this guy. You tell me that it's not a zappy flash route. 100% zappy.
All right, if you want to follow along in Figure 14, but I will be drawing all of them, so you don't really different time.
It's like battery. I guess it's.
You should charge your shit.
I didn't have time.
I don't know that.
Figure 14.
Boy, I looked worse and it was only almost it's 15.
14, baby. Oh.
All right, so in this example, we've got our capacitor here. This empty space will be the capacitor. When we close this loop, that will be the capacitive current. So when we close that loop, which way does current flow?
Yeah, counterclockwise.
Counterclockwise? Counterclockwise?
Hold on, what is the
It's gonna
I
flow
see?
towards the plate.
I is current. C subscript means capacitive. So what does that mean? Which way does the current flow?
Clockwise.
Towards the positive.
Yeah. So when that switch closes, current will be flowing clockwise because this is your power source right here, and it is 10 volts. So what this is going to do is it's going to pull electrons from here and bring them here because this is positively charged. Electrons are negatively charged. And this will force electrons away from here to here because it's negatively charged. So what you're going to end up is a capacitor that is negatively charged on one end and positively charged on the other end. Now, when we cut the power and let the capacitor empty, which way is that going to flow?
When we what?
When we cut power, when we turn off the power source and let the capacitor drain, which way is that going to flow?
Counter.
The current. Which way will the current? Which way will the current go after we cut off the power supply?
Like counter.
Counter, same. Same. Why is it counter tie?
It's trying to equal out
What's trying to equal out?
the electricity. It's going to equilibrium. The electrons.
So once this power source is gone, you no longer have this power source forcing electrons here or pulling electrons away from here. So now you have a built-up negative charge here and a built-up positive charge here. So now all of these will return, and everything that was pushed over here is going to get forced back. So a capacitor is going to work in the opposite direction once it's activated. Also, before then, so like
It's going back to equilibrium. You just said once activated.
no, once the power is once the capacitor is activated, once it's discharged. For the discharge,
I don't know what.
before the discharge, if you had this, no power coming in, you just had the capacitor holding its charge. If you put a meter lead here,
Can you draw this in any way, like using that, like image of a capacitor that I can like see?
okay, yeah, sure, give me a second. If you put this to a meter, what is the meter going to read here? Meter here.
With the voltage on?
Oh no, wait, this is off.
0. Nothing.
This is after it's collected a charge.
Whatever. 10 volts probably.
Yeah, it'll be 10 volts because it's one thing you guys are gonna have to understand. There's potential difference. The entire point of everything for electricity is potential difference, and whenever something seems confusing, it's probably because the answer is like you have to think of as a frame of reference the potential versus what you're looking at, and you're just missing a piece. So like the potential difference here from here to here is 10 volts because 10 volts is what separated this, and so now the only thing keeping it apart is that dielectric material, and so the potential difference from here to here is 10 because if you were to bridge that gap, you would have 10 volts across. That's the potential basically. Let me see. All right, so the reason I bring up the potential difference is that's when it'll stop charging. So when it comes up to the point where 10 volts only gives it enough power to separate 10 volts worth of potential difference. Once it reaches that amount, everything else, all it's doing is just maintaining, or really just completely wasted. So if you wanted to store a bigger charge, you would need more initial charge. The capacitor can be discharged by connecting a. That's for DC one, by the way. The charges until a potential difference across the capacitor is equal to the applied voltage. The capacitor can be discharged by connecting a conducting path across the dielectric material. So what you were asking for in the picture. So So if we cut this on, this is the negative, and this is the positive, right? So having this power source on, the current is flowing this way. Current flows with electrons.
What is an example of this power source?
Anything
Like when do you use a capacitor?
Single phase motors.
We'll get to capacitor usage later, but knowing where the power comes from won't make any difference to understanding this.
You was like a toast.
You're still in charge.
Yeah, okay. So, Austin, just let me do the explaining, please. The electrons are getting forced over here. They can't cross this barrier because this is the dielectric, right? So they're forced over here as much as they can be. They hit this barrier, they can't go any further. So they build up here around on and around this metal plate that we have in the capacitor.
Why were they forced over there?
It's electricity. Electricity is the movement of electrons. This is your power source, it's forcing electrons over. That's just how electricity works. It pushes through electrons. I mean, like, you don't have to nod. Like, if you're not getting it, you understand?
Mm.
Actually, okay. On the other side, it actually has a shortage of electrons, which we notate with the pluses. It's not adding anything, but the electrons that were there have been pulled away. So what's left is a positive charge gap where they were. You understand? So this was at 0. If you have 0 and you subtract -10 from 0, what do you have?
-10.
You subtract -10. So you have +10, right? So each electron is -1. You pull out 10 of them because this is a 10-volt charge. So you pull out 10. You pull out -10. You're left with +10. So now there's a gap of 10 volts on this side because all of that.
I want to make sure someone knew that the battery was dead to that point.
Okay. So all those electrons are over here now. Okay. Does that help?
So it starts off with the minuses on the top.
It starts off with everything at 0. It starts off with this is 0. That's 0. Everything is 0. You apply the charge. You have electricity now. This is a DC with positive and negative terminal. So it forces the electricity in a specific direction. So this side's negative, it's forcing the current this way, which means it's forcing the electrons this way, which means this spot here will end up with a positive charge of 10. This spot here that was neutral, it was positive. Well, neutral, it was just neutral, it was 0. It's now negative because all those electrons from over there have now come here. So now this is at -10. This, which was at 0, was neutral, it was at 0. This is now turned on. This is a positive force, meaning there's a void of electrons. And nature moves to fill a void. So like now all those electrons that were here are attracted to this positive charge. So now they leave, leaving behind a positive charge. Because that's what happens when you minus a negative. And all those electrons end up over here. Until you cut power and reconnect the circuit, and then it all snaps back in the opposite direction. All right, what's not getting? What's All right, tell you what. Here.
I like my brain's trying to think of like a battery or something. Like I know this isn't battery. Like
He
what?
needs a physical example that he knows. This is a toaster oven. This is a transformer.
The thing is, capacitors are just kind of niche. They don't really have a purpose like that. You would never just use a capacitor by itself.
When are we going to use a
So that's
capacitor?
like
in
a
the field?
battery where like you can actually
No,
charge
because
one end
no,
and,
because
keep
like
up that.
this holds a charge, but it's just that one charge. As soon as you connect that to something, it lets it go all at once.
What's a real world example? of that?
Like you ever open up a computer or like any kind of electronic device, and there's gonna be, actually you've probably seen it in the field. There'll be a sticker where it'll warn you that there's a capacitor in there, and that the capacitor can kill you even if it's not connected, because the capacitor is storing a charge, and if you touch it, like everything that it's stored will hit you at once.
How is it storing it? Is it connected to that power source then?
So like right now in this state right here, it has a charge. This is a stored charge.
Yeah, I get that, but
So I mean, normally they
so
would,
it's
normally there
connected
would
to
be a
that power
switch.
source, and
So you close the switch, it charges up, then you can remove the switch, and it'll still have that charge. This is obviously like super simplified. In a real world use, it would have a second circuit that you connect to it instead of this one after it's charged. This is just like the simplest possible version, just to show you how it works. So like if this was a real world example, there'd be like a second switch here that connects this to a completely different circuit. So this circuit is just to charge the capacitor, and then when you need to use the capacitor, it would connect to something else and let the charge out. It wouldn't release the charge back to the same place it came from, otherwise it's like, what are you doing? Did that help at all? Like you still have... Alright. Okay, so that's with a DC power source. What would happen if we connected it to an AC power source? Austin, let someone else say something. I will look at you when I want an answer from you, okay?
Am I doing good or am I doing bad?
You're doing fine, but you keep sniping answers when I'm trying, like, Aiden is obviously struggling.
Sorry. I mean, you want me to go to third year or something? I'm good. I'll do it this year. Maybe in first year.
Austin probably tested out a year too, right?
All right. Well, what would happen in an AC circuit?
Fluctuate.
Yes. Thank you, Aiden. Why would it fluctuate?
Because that's what it's alternating current.
So yeah. So give me the step by step.
Give me the step by step.
Explain what you just said. Wait, the way I explained
So
something.
it would
Okay.
alternate, go that way.
So it would start positive,
Uh-huh.
and it would charge the
Yeah.
capacitor.
Yep. But then we'll go back to zero,
And
and
then-
then it would draw everything out, neutralize it again, and
And-
then it's going to go the other way.
Yeah. So all right. So in with AC, that is what it does. It's basically just a constant cycle of back and forth. And so while the AC is positive, it's charging the capacitor. Doesn't matter. When it's positive, it's charging the capacitor in one direction. When it's negative, it's charging the capacitor in the other direction.
Yeah.
So it's just constantly like circling back and forth.
So that's pretty useless, right?
No.
There are uses for it. Well, that's good goal for that. So here, what's happening on the capacitor?
It's going.
So this is the sine wave for the AC. So this is not the capacitor. This is the sine wave for the AC. What's happening to the capacitor during this stage of the sine wave? How voltage is increasing, right? So this would be connected, and this voltage would be increasing. So if this power, that means the charge is increasing. So during this 0 to 90 stage, the capacitor is charging. From 90 to 270
It's neutral.
That's right. Remember, this. I'm asking you what the capacitor attached. So the capacitor is this point.